Hey guys, and welcome back to this video on Turd Ferga Vision. So as we're taking a look at it, somebody sent this one in, and I actually decided I would work it. I don't always take user requests, but this one actually did seem worth it because typically we see a problem like this. It's a beam on like the side of a building or something, and there's usually like a cable attached on the end of the beam, and so like this, that is standard. You're going to see 101. This one is a little different for two reasons. One of which instantly being the fact that this beam that is in this problem is obviously not perpendicular to the side of the building. And so this one actually looks like it should be fun. So let's do something real quick. There's a couple of forces missing from our picture over here. Normally I like doing those in red, but since this one, I'm going to do it in blue. So we know we have a tension off the side of this, and it's already told us the value of that tension. We know that every beam should have an mg going straight down in the middle, as long as the word uniform is used. And then typically, notice how I keep saying typically, there is a reaction force at the wall, at the pivot point y, and typically, and this is where this one does throw into another problem, typically we have an Rx, a reaction force that way. There's just one problem with drawing this picture. So if we check it out and do like a little looking here at this problem, and we sit here and like look at the angles involved. So let's see, this angle would be a 30-degree too, which means that that angle would be 60 degrees on the other end. So check this out. In terms of doing a sum of the forces x, look at why we would have a problem right here. We would have a t cosine 60 going right, and we would have a plus Rx right equal to 0. If you've learned anything so far, you know that can't be right. Something can't be in static equilibrium and actually have two forces in the same direction. Well, I know the t cosine 60's got to be right, so that means this Rx, I've got it wrong. That's going to have to be a minus Rx for this to work, which means if I go back into this problem, the Rx was not to the right, but my reaction force has to be to the left in order to make this problem balance. So that's kind of weird. Didn't expect that when I first saw it. And so now how about some of the forces y? We've got a t sine of 60 pointing up. We've got plus an ry, and now minus an mg, and we can set all that equal to 0. All right, so that looks good. So now here's the problem, though. We don't have, actually, we've got enough problem. We could go ahead and solve this problem. I don't know what it asks, but let's look. Normally, this should be a torque problem, but check this out. If t is equal to 20, that means 20 cosine of 60. Oh, we can't do this problem. 20 cosine, oh no, we can do this problem, assuming we've got a mass in there. T cosine of 60, gee whiz, sorry, would be equal to Rx. So cosine of 60 is a half, so that means my value for Rx would be 10 newtons. Okay, well, that's really pretty easy. I'm going to check the problem real quick. So I went and double checked, and this problem actually asks to find the weight of the rod. So we're looking for that mg. Now here's where we're going to need a sum of the torques, because when you look at the sum of the forces, we know T, but we don't know Ry or mg. So we're not going to be able to work this one. So we need to do this. We need to now go and make a sum of the torques. So what would the sum of the torques be acting on this object? Well, first we need to pick a pivot point. And I'm going to be honest, there's not a good place to pick a pivot point in this problem. If you remember my joke, it's always pertinent when picking pivot points to be precise. I wish I could get more P's in that. But anyway, let's go for green. I usually always pick the wall to be my pivot point. And because what that's going to do is that cancels out the Rx and the Ry. And it means I should be pretty good in this problem, but the trick is going to be this. Remember, when you're doing torques, you need to always know the angle. Well, this one's great because that one's 90 degrees. So that one's just T times the length of the beam. So check this out. I know that this torque, we'll call it 1, and I know that this one we'll say has a radius of a half. So what is the angle on this MG? So now we're going to have to figure that out. So I'm going to try and draw that angle a little bit straighter because I'm going to have to see something here. So, oops, that's going to be a really, really big. So there we go. Straight down. And let's see if you can play the game with me. Can you figure out the angle in this problem? Well, let's look. If that's 30, we know that angle is also 30, which means this angle is 60 degrees, which tells me exactly what I needed to know. Because to do the torque, it's going to be the perpendicular. So here's what I'm going to do. I've got two torques. They're in opposite directions. So I'm going to go with the clockwise torque force, which would be this mg. So I'm going to have mg sine of 60 times the radius of a half minus my other torque, which is T times, well, actually it's just T times R, which would be 1, and it's all equal to 0 because it's balanced. So check it out, guys. This problem's actually really nice. We didn't even have to do the sum of the forces. Sum of the torques we've already done. There's no sense in rewriting that. So let's look at what we've got. We're looking for mg. So we're looking for mg. Sine of 60 times a half. Let's see, that's 0.86 times a half. So that would be 0.433. So that's 0.433. And I wrote mg. You could write w. And that's going to be equal to T times R. And we know that T in my case is 20. R is equal to the whole length of the rod. So 20. So this one's going to be great. 20 divided by 0.433. And we got 46.1 newtons. So the mg, wow, my screen just went totally crazy. So my mg, thus my weight, or my force gravity, whatever your teacher wants, we just said is what? 46.2. There is the weight of my rod, guys. And also, if I wanted to know what Ry was at this point, I know T. I now know that mg is 46. I could plug back in, and I could find my reaction force Y. Anyway, guys, that was kind of a cool problem, so thanks for watching.